In this video, we explore the information available in the Mozilla Firefox crash reporting system, using it as our example. While we focus on this system, it's worth noting that many other crash reporting systems offer similar features. This slide presents crash data from the Firefox browser, specifically focusing on crash statistics per active daily user and the top crashers for different versions of Firefox. The chart visualizes the stability trends over several days, helping developers monitor and compare crash rates across pre-beta, beta, and stable versions. On top we can see crash rates per daily active user. We have three lines. Blue line is the pre-beta version, 4.0b8 pre. It exhibits the highest crash rates, indicating its instability. Green line is the stable version, 3.6.12, and it shows the fewest crashes per active daily user. Red line is the beta version, 4.0b6, that sits between the other two. Lower parts show the top crashers by version. Specific crash causes are detailed for each version, helping developers identify recurring issues. For example, in pre-beta version, _PRMDSEND is the leading crash reason with 584 occurrences. In the stable version, user callwinproc checkwow is the top contributor to crashes, with 109,448 instances. Before we proceed, let's pause to examine where the data originates. In Firefox, crash data can be accessed by typing about :crashes in the address bar. Similarly, in the Chrome browser, crash data can be viewed by typing chrome:/crashes into the address bar. This will display a list of crashes that have occurred on the machine, along with an option to manually upload reports if crash reporting is disabled. Take a moment to review the crash history details in your browser, and then return to the video. Back to the Firefox crash data. Clicking on a crash signature such as virtual allocx provides developers with detailed information about the crash, including its stack trace and related metadata. After clicking the crash signature, we are presented with a detailed view of crash reports for the specific signature. The line graph shows the frequency of crashes over time, segmented by different operating system builds. In this case, the crashes occur exclusively on Windows platforms. On the 3rd of November, we notice a spike as a buggy version is released. By the 11th of November, a new build resolves the issue as the crash frequency drops significantly. Continuing with the same crash signature, we select the Reports tab. This allows us to view individual reports. By clicking on any report, we can access its detailed information. This view provides detailed information about an individual crash. At the top, we can see product and software context details, including the crash signature, operating system, and hardware information. Below, the crashing thread is highlighted, showing its stack trace with the exact functions, code lines, and modules involved. Further down, we could see a list of other threads that were running at the time of the crash, offering additional context for debugging. Going back to our previous research data on missing or incorrect defect reports, we can see that 50% of the respondents thought that software context information was quite often or more frequently missing. This context information, however, is automatically collected for this report. As shown on the screen, we can answer questions like what version the user was running, what operating system they were using, and what other crashes this user has experienced. Clicking on the Extensions tab provides a detailed list of all extensions or plugins that were running at the time of the crash. This includes information about their IDs and versions. This data helps identify if a specific extension might have contributed to the crash. Moving from individual reports back to the crash report signature level, clicking on the Correlations tab provides insights into the modules associated with the crash. This tab displays the percentage of crashes involving specific modules relative to their occurrence in all crashes. For example, some modules might appear in 100% of crashes for a particular signature, but are present in only a small fraction of all crashes, indicating they could be contributing factors. Referring back to our previous research data on missing or incorrect defect reports, we now focus on stack traces. The data reveals that 54% of respondents reported that stack traces were often or more frequently missing. As shown on the screen, this information is automatically gathered by the crash reporter. The detailed stack trace provides a sequence of function calls leading to the crash, including information about modules, function signatures, and even links to specific lines in the source code. User comments are optional, but they can provide valuable insights if they tell a consistent story. In this case, a user comment is included in the crash report, offering additional context or clues about the circumstances leading to the crash. While automated data collection is essential, user comments can complement the technical details by sharing observations that might not be captured automatically. This view connects the crash report to the defect database, in this case, Mozilla. By clicking the bug ID, developers can directly access the corresponding defect report. This integration helps link crash data with ongoing or resolved bugs. Here, we see the current architecture of the Socorro crash reporting system used by Mozilla Firefox project. Socorro, which means help in Spanish, is an open-source crash ingestion and analysis platform developed under the Mozilla public license. The diagram illustrates the flow of crash data starting from the crash reporter client, moving through AWS infrastructure for storage and processing, and ultimately being analyzed and displayed in a web application.